In lesson 11.5, we're going to talk about proportions like we've been doing in the past. Remember, the phrase proportions is basically saying two ratios that are equal to each other. Or, for example, to be very general and vague, I guess, I'm saying like A over B equals C over D. Or if you want to see them in numbers, you could say something like 3 over 6 equals 7 over 14. So when you have two fractions that are equal to each other, the fractions themselves are called ratios, but when you set them equal to each other, that's called a proportion. Now, the interesting thing is, whenever you look at this kind of stuff, sides, when you look at corresponding sides of two similar polygons, they always have a ratio of m over n, which means a length, like 3 and 6, for example. So this is talking about what you see right here, 3 and 6. But whenever you see something to do with areas, then the areas are in the ratio of the m and n squared. So what you would then say, if I was looking at it this way, is I would say the 3 squared compared to the 6 squared is how those sides would be compared. Down below, we can see some pictorial representations of how this works. So if I look at the top rectangle, which is a 2 by 3 rectangle, and the bottom rectangle, which is a 4 by 6 rectangle, what I notice is that if I compare the side lengths, like for example, the 2 and the 4, as an example, that's the same comparison as the 3 and the 6, right? And this ratio that I see is a 1 to 2 ratio. What does that mean? That means that everything that I see going from the top rectangle to the bottom rectangle has been doubled when you look at specifically the sides. But look at what happened. So when I look at going from the side in this first rectangle to the side in the second rectangle, I'm doubling that information. But look at what happens when we check out the areas. So now if I look at the area from the first figure to the area of the second figure, I've multiplied by 4, not by 2. Why? Because area is length squared. So if I were to take this 2 and square it, that's how I would get 4, which is the way that I would go from one area to another area. So the side length would be doubling, but the area would be squaring that number. So if you find out to transfer your side lengths from one figure to another, for example, let's just say I draw rectangles off to the right here. Sorry, let me give you another example that might help a little bit more. So I draw a rectangle, here it is, and I draw another rectangle, here it is, and I tell you that this rectangle has a side length of 1, and this rectangle has a side length of 7. So I know that going from the 1 to the 7 means that my side lengths were multiplied by 7. And then if I told you, hey, in that first triangle on the inside here, the area was 3. And then the question is, how big is the area in the second rectangle? And I know that in order to find that out, I would take that 3 and I should multiply it by something. But I don't multiply it by 7, which is how I got to the next side. I multiply it by 7 squared, because I'm dealing with area in square units. So the ratios would be in squares of each other, not just in the number themselves. So 7 squared is 49, and 49 times 3 is 147. So this 147 would then be the answer to my question, which is, how big is the area of the second rectangle? So when you go from side to side, that's a ratio of m to n. But when you go from area to area, That's m squared to n squared. Or in other words, square the number that you were using for the sides to multiply by. This also works in volumes, but instead of squaring, this time we cube. So again, looking at the corresponding sides, we have mn, but looking at their volumes, we have m cubed n cubed. So what does that mean? In practical purposes, what that means is I look at going from one side of 7 to the other side of 14, I am doubling the side, which means I'm multiplying by 2. But when you look at volumes, to go from 42 to 336, I'm multiplying by 4. Why? Because this is the 2 that I was using for the sides squared. Or sorry, pardon me, cubed. And what I should have said is not multiplied by 4, but by 8. Pardon me. I said squared because we were just in areas, but now I'm in volumes. So if I take 42 times 8, I get 336. Why is that? That's because the side ratio was 2 times as big. But when I'm talking about volumes, it's a cubic. So I cube the 2, which gives me 8. And so to go from one volume to the next volume, I multiply by 8. Let's say I was looking at another example, just like I did in the previous slide, just to kind of hit it home. Let's say I had some kind of volume that I was going to do again, and I'm going to draw a different figure altogether. Let's say I'm doing a cylinder. And in this cylinder that I have here, I have another cylinder down below. And I know that from the first cylinder, 1, going to the next cylinder side is a 3. So that's the side lengths, or in other words, I multiplied by a 3. And I tell you that the volume inside the first cylinder is a 5. In order to find the volume of the second cylinder, what I would have to do is I would have to take the volume of the first one, which was 5. I'm looking up at the top now here to write this down. So I take the volume of my first cylinder, 5, and I multiply it by my 3, and I would have to cube that. So I'm going to highlight each of these so you can see where they're coming from. First of all, the 5 in red highlight is the volume of that first cylinder. Second, the 3 is the side ratio. And lastly, the cube is because I'm working with volumes. So I have to use that side ratio 3 times. Or in other words, multiply 3 to the 3rd power. Now, if I do this and I multiply that out, I would find out that the volume of that second cylinder, that is 5 times 3 to the 3rd power, would be a total of 135. And so that's the volume of this bottom pink cylinder. So when you're working with sides, it's linear. They call it M to N. When you're working with areas, it's square. That's M squared to N squared. And when you're working with volumes, it's cubes, M cubed to N cubed. And in this particular figure, which is kind of nice to see, you can look at the comparisons of the sides and then look at how their volumes compare. And they're all the same as far as what's going on. So let me just point this out to you. I'm looking at the side ratios down at the very bottom. And what I notice is that all these side ratios, 7 to 14, 3 to 6, 2 to 4, they're all in the 1 to 2 ratio for volumes. So this number is always saying 1 compared to 2. Or in other words, the second figure is twice as big as the first figure. As I look at the other numbers, 7 cubed to 14 cubed, 3 cubed to 6 cubed, all those numbers, if I look at those ratios, 7 cubed to 14 cubed, 3 cubed to 6 cubed, 2 cubed to 4 cubed, all of these ratios are 42 to 336. Now you might not realize that, but if you were to simplify that fraction, you would see that these are all 1 to 8 ratios, meaning that the second figure has a volume that is 8 times larger than the first figure.